Okay, so I hope everybody's safe. I mean, well, don't worry about the coronavirus situation. Hopefully everything will go okay. So we'll finalize the point of why the method of Lagrange multipliers works. I kind of like made some geometrical intuitive argument, but let's just formalize it once and for all. So the geometric argument was along these lines, that for any function that we are going to call for the moment capital F of x and y, the level curve of the form, of course, since a level curve f of x and y equal to c, has a slope at each point x comma y given by dy over dx equal to minus the ratio of fx divided by fy, provided that fy is not 0. Now, if you wonder where this formula comes from, there is kind of like an easy hand-wavy way of looking at this, which is that let's assume that you're in a level curve, which means that along the points in the level curve, f doesn't change the value and it's always c. So that means that if you consider the change in f, it will be 0, because it always takes the value c along the curve. And if you use the chain rule, what you would have, this is equal to fx dx plus fy dy, since f is a function of x and y. So along this path, the change in f is 0. And basically, if you use this formula to find the y over dx, you get this. Just some manipulation. The argument is hand-wavy. I don't think this in particular comes in the book, so hopefully it will help you a little bit. But in any case, the formula comes from there. So, in particular, for the constrained optimization problem, the goal is to minimize a function, which is little f of x and y, subject to the constraint that we call g of x and y equal to k. That is just a restatement, but I'm trying to tie this concept of the level curves into our problem. And again, geometrically, the geometry of the argument in terms of the constrained optimization, where you use Lagrange multipliers, is to find the highest level curve value. So basically the highest value of c if you want to maximize, or the smallest if you want to minimize, but you get my point, of the function f that intersects the constraint that is the curve g of xy equal to k. And so we made a picture trying to anticipate the concept, which is quite illuminating. You have the x-axis, the y-axis. You have a constraint curve that I'm going to draw now. So this is the geometrical representation of the so-called constraint curve g of xy equal to k. So this is the equation of the constraint. And then you consider the level curves of f, right? So for example, one level curve similar to the optimization problems that you saw before could be this, right? So, okay, it's a curve and it has a given value. But of course, I want to maximize f under the constraint, meaning that I want to find along these points that satisfy the constraint, the points or the point which has the biggest value of f. So let's assume that if you move in this direction, the level curves have higher values. So let's say that, for example, I could have this other curve, right? There's an issue with this one because you have gone to green. You have an increased f, but it's not intersecting the constraint, so this is not a valid answer. So you have to look basically for the curve, if you were to do this representation of the level curves, the one that maximizes and kind of like touches the constraint curve, which would be, for example, this one, right? So, I mean, this is like a thought experiment. We will call this the direction in which C increases for, well, f of x, y equal to C. So we have different level curves. We increase C, but we want to still be in the constraint, so there will be at least one single intersection. And moreover, the curve of the constraint and the level curve over this point will be tangent. So they do not only intersect at the point, but they touch each other, like they kiss if you want. And when you have that relation, essentially, since they are tangent to each other, they would also have, I will have to use the red color for this. Well, they would have the same slope, right? So is that intuitively clear? You see why? The curves are kissing each other. So since they're touching, they're tangent to each other, so that means that they share a common tangent line, which means that they have the same slope. And so now we will express mathematically this geometrical intuition in the following way. So this is a so-called, basically this is a point of tangency. And this particular curve is the highest level curve, f of xy equal to C, that intersects the constraint. So we will call this critical intersection, and it happens at a point where the constraint curve is tangent to the level curve of f. So the slope of the constraint curve, which is g equal to k, is equal to the slope of the level curve f of xy equal to C. Now, why do I bring this point? Because this formula, we're basically indicating the tangency of this level curve with this level curve. And we have a formula that we derived here for basically the slope of a given level curve. And capital F can be g or can be little f. So we will use that formula because we know that the slopes are equal for these two curves at this point. Okay? So that's what we will equate. So since on one hand, if you want to formalize the argument, you have that 0 is equal to dg, which is gx dx plus gy dy, which, well, that is because you have a level curve, and that means that dy over dx for that curve is minus gx over gy, which is what we derived above. And on the other hand, you have that you're sitting on the level curve that maximizes the value of f, which is still a level curve. So that means that the df is equal to 0 of little f. So fx dx plus fy dy is equal to 0. And from that, you can derive that the slope is minus fx over fy. So this is how you're equating the slope. The slope of the level curve related to the constraint is equal to the slope of the highest level curve that maximizes. And so from this, well, I can eliminate the sign, etc. You have that fx over, well, you can pass to the other sides, etc. So fx over gx is equal to fy over gy. Just take the minus sign, basically pass dividing the gx and pass the other to the other side, and you get this relation. And we're going to call this ratio lambda. Okay, so the ratio of these two quantities is the same. It's at the point of tendency, so it has a given constant value. It's the same, and we're going to call it lambda, which is not coincidence because this is the Lagrange multiplier that appears in the equations. But at least there is some geometrical argument for why it is happening. So if you follow along these lines, what you conclude, just passing to the other side, fx is equal to lambda gx, and fy is equal to lambda gy, which were the first two of the three Lagrange's equations. So at least you're basically, if you think in a more abstract, logical, mathematical way, tangency of level curve with tangency of the constraint gives me this relation, or these two relations. And the last Lagrange equation is simply a restatement of the constraint, g of xy equal to k. So this is just constraint, and the three of these form Lagrange's equations. But you see, actually the geometric argument is quite powerful, or at least very illustrative of what you're doing, because the change from the previous problems of optimization to this one is that you're maximizing under a constraint, which means that you want to find the maximum value that satisfies the constraint curve, which is looking along the points of the constraint curve, which has the maximum value of f. And this way of moving the level curves into finding or exploring higher values, it's basically giving you the condition. And the condition of tangency for the level curve of f that has the highest value in order to maximize, and the other gives you two of the first three relations. And the third one is a restatement of the constraint, and you're done. So I think the proof is very intuitive for a concept that doesn't come pretty clearly, because we modified basically the function at the beginning in order to define a new function of three variables, x, y, and lambda, do the criteria of the critical partial derivatives, finding two of those three equations, and the third one, when we introduce this new term in the function to be maximized, gave you the constraint. But now it's clear why it's happening. So hopefully, as long as you understand the picture, you can derive it by yourself. I think so. Basically, if you understand this key point of tangent curves having a common slope, everything else is just a math formalization. So, okay. I finished presenting the concept that I started in last class, and having said that, okay, we have finished the topic of constraint optimization, and we will start actually a new chapter, which is 9.1. So this would be introduction to differential equations. And actually, look, I do like this approach of the book. Even in more mathematically powerful calculus textbooks, such as, can you see okay? Okay, now it's focusing. Look, there is a fabulous calculus book if you want to go like all math-oriented, which is basically the book of Richard Courant. There's a lot of stories to mention about that. But his approach is basically to combine math and physics. And in the last part of the book, you actually also have an introduction to differential equations. Usually, a course in differential equations would be a second-year course or a third-year course. But that shouldn't scare you, because a DFQ, loosely speaking, is just an equation that involves the derivatives. And you have found plenty of those in the modeling that you have done so far, especially when you have considered the exponential growth model, like the Malthus model, when you have considered the logistic model, etc., etc. So I like the idea of getting the hands dirty and not being afraid just because it's a second-year course. You will see that we have seen many of the concepts, but the idea will be to formalize what is a differential equation, to introduce some of the terminology, and then to see that we have actually solved some of those examples. So, a differential equation, we can also use the abbreviation DFQ or DFQs. Sometimes you also use ODE, but that's mainly to distinguish between ODEs and PDEs, because the kind of differential equations that we will deal are so-called ordinary. There are more complicated differential equations, which are called partial differential equations, but that I don't think we'll see in this course. But in any case, the differential equations, as the name says, they are equations that involve the derivatives or differentials of functions. Now, why have I said that you have seen this kind of stuff before? Well, because I will write 3 examples of diffs, and you will see that you're actually quite familiar with that. For example, dy over dx 3x squared plus 5. If I tell you to integrate this, you know how to do it. Well, solving the dfq amounts to finding the function y of x that satisfies that. And that's basically an exercise in integration from the previous chapter. Now, the reason dfq is actually a subject course in the second year is because the equations get more complicated, and you have to develop in a first ODE course all these techniques in order to solve this problem. So it's not always as simple. But the idea, loosely speaking, is definitely to find an integral curve that is a solution to the equation. Another example, for example, is dp over dt equal to kp. If I present this to a population biologist, this is a population model where I have the Malthus exponential model, right? The rate of change or the rate of growth of the population is proportional to the population itself. That is the Malthus model that I have in bacteria. Then let's say I write another equation, dy over dx squared plus 3 dy over dx plus 2y equal to e to dx. Okay, that actually might be a little bit more complicated than what I have done before. But still you get the idea. You have an equation that involves the derivatives of the function and you want to solve for y as a function of x. So in any case, dfqs in general, they appear in mathematical modeling due to the study of rates of change. The same way, this is trying to present you the dfq topic from a modeling part. It's equivalent to say, well, if you think of as a population biologist, you have seen this equation before. And why do you care about it? Because you want to study how the population evolves over time, which means that you have to consider the rate of change of the population with respect to time. And this is the Malthus model. So these models are pretty common. Now, we will have to define some terms. So please hear the following terminology. So the first one, it sounds trivial at the beginning, then it will get more complicated. So, well, what is a solution? Of course, so a solution is a function that satisfies a given differential equation. Now, okay, this sounds trivial, in a way it is. But the reason they're telling you that is because there are 2 kinds of solutions, which is essentially, well, think about it this way. When you integrate, in one of the previous exercises, you always had a constant of integration. You don't know the value of the constant. And that constant is defined from the conditions of the problem, like an initial condition. So there are 2 kinds of solutions. A general solution, which is the one that has a constant of integration, because formally speaking, what you have is a family of solutions in which the parameter is this constant of integration. So changing the value of c, you get a new solution. And then if you have a particular value of the constant, you have a particular solution, which will be a solution for a particular initial condition, which is, for example, what is the value of the function at the initial time, or at x equal to 0, or at x equal to 1. So that's the difference, and that's why the concept is mentioned. So the general solution of a dfq is the characterization of a family of solutions. Now, what is an initial value problem? And I'm pretty sure that I talked about this IVP like 1 month ago. So that is when you have a differential equation, a dfq, but it's coupled with a side condition, which, for example, if you have y in terms of time, say, for example, if it's a condition at the initial time, it's called initial condition. I just make the distinction because not always the independent variable will be the time. You can have a differential equation where x is a position instead of a time. So the physics is a little bit different. But in terms of the kind of problem, you still have an initial value problem because you want to evolve most of the times. So then we have another kind of solution, which is called the particular solution. And it is called that way if it satisfies both the DFQ and the side condition that sometimes we'll call initial condition. Look, actually, initial value problems are not the only kind of problems that appear in DFQs, even in 1D. If you have heard of something called a boundary value problem, it's because interpretation is different. You can study, for example, let's say that you have a material, which is a rod, and you can heat it on one side, right? So let's say that you want to study the temperature of the rod across the horizontal domain, but you, being the experimentalist, you have a control of how the temperature changes on one side. So that would be an example of a boundary condition. So it depends on the kind of variable that you have. There will be some problems where we will talk about initial conditions, so don't worry. So the next point after these definitions is that for equations of the form dy over dx equal to g of x, we can solve this DFQ by finding the indefinite integral of g, which is what we have done before, right? Usually, I apologize if it's not focusing frequently. Usually I give you like a nice function g, like a polynomial or a log function or an exponential function, etc. And you know how to solve this problem, which is integrating. So you're familiar with this. We will do an example just to basically comfort you in the sense that you have some experience with this kind of problem. So this is 9.1.1, which is solving an initial value problem. And the statement is to find the general solution of the differential equation dy over dx equal to x squared plus 3x. So for this problem, because it's very simple, I mean DFQ is a fancy name for what we have to do. We just have to integrate. So we all have experience for this. Now there is a second part in the statement, which is that you notice that they are telling you that you have to find a general solution, which amounts to indicate that you have a constant of integration. Then you also have to find a particular solution that satisfies the condition y equal to 2 when x equal to 1. Okay. At this point, I'm not calling it initial condition because I don't have the interpretation of x as a time. It's just a 1D variable. So the solution is, of course, obtained by integration. So integrating, what you have is that y of x, well, integral dy over dx, so the integral of the derivative, that is the fundamental theorem of calculus. Then you have integral of x squared plus 3x dx, so you have x cubed over 3 plus 3x squared over 2 plus a constant of integration, right? So again, these are the kind of problems that we have done before. Now, this is called the general solution, precisely because, well, all solutions of this equation can be expressed in this form on one hand, and on the other, don't forget that you have this parameter, which is the constant of integration. So C is a real number, and it can take any value. I mean, whichever value of C I take, it's still a solution. So clearly I don't have, in general, one single solution, but I have a family of solutions where each one of them is defined by a parameter C, which is a real constant. So of course, okay, I have many possibilities, but if I have something like this side condition, like the condition y at a given point x equal to a value, that will define the constant of integration the same way we jumped from indefinite integration to definite integration. So now, when we will talk about a particular solution, it will be one such that y at 1 equal to 2. If you notice, the condition is the particular solution is the solution that satisfies the condition y equal to 2 when x equal to 1. So this is just that same condition. The way to obtain the particular solution is, of course, to define the constant of integration. And that just amounts to the same thing that I did before. 2 is equal to y of 1, and I have to plug in this formula, right? So basically 1/3 plus 3/2 plus c. And that will define my c for this particular solution. So basically c is equal to 2 minus 3/2, minus 1/3. Have to make a division between this. So here I would have 1/2, making the difference between these two, and then minus 1/3. So if you do the fraction, you have 1/6. So that would be the constant. And then the particular solution would be, in that case, x cubed over 3 plus 3/2 of x squared plus 1/6. So this is the particular solution. But this is illustrating why we talked separately between general solutions, where you have basically all possible solutions of differential equations, and a particular solution that satisfies a given condition. It gets more complicated. There is a lot of theory for linear differential equations. It's not an easy topic when you make the difficulties more complicated, but at least for something that you will see later on, perhaps in linear difficulties, usually you have, let's say, one constant or two constants of integration. For example, when we did a physics problem where we jumped from the acceleration to the position, basically you have second derivative, first derivative function. In that case, if you remember, we had to determine two constants. That was because we had second order derivatives. And for those kind of problems, usually second order problems need two constants of integration to be determined. In this case, you have only y prime. You do not have y double prime appearing in the problem, and that's why you only have one constant of integration to be determined. But as long as you're distinguishing between the general solution and the particular solution for this simple problem, it is achieving the purpose of the exercise. So, is there any question? Okay. So you see, I mean, part of the idea of these exercises is to show you, well, I mean, you should not be afraid of this topic because you have done this before. Of course, it can get very complicated, so that doesn't mean that the topic is trivial. But, I mean, look, if you're an economist, population model like the Malthus model or the logistic model will also appear. You don't need to be only, a biologist. Moreover, actually, and I say this because of the times that we're living, there is actually a set of differential equations that model epidemics. That is called the SIR model. So you can use this kind of object actually to study some real application phenomena. And if you see in the news that people talk about this R0 number, that's basically a parameter that appears in that epidemics model. So it's not that far away from real life. In any case, so the next example is quite applied, is to determine the Resale value a machine. And so quickly, the statement of the problem says that the resale value of this machine decreases over a 10-year period. At a rate that depends on the age of the machine. I mean, it can be any kind of machine, right? The quickest example that comes to your mind is probably a car, right? When you buy a new car in the agency, of course, it decreases its value. That totally makes sense. So when it's X years old, its value changes at the rate, so that information we're given, somebody calculated it for us, of 220 times x minus 10. So think about the terminology, okay? And the units are dollars per year. So the first commandment is to express the value of the machine as a function of its age and initial value. Of course, I mean, for a car it's pretty intuitive, right? I mean, what is the price of the car and how far it goes? Actually, whenever you have a car towed, actually the insurance company has a software that, depending on way too many variables, like the brand of the car, the year it was bought, conditions, etc., it will calculate what is the current price. So that you probably know. Okay, you have to calculate this if the machine was originally worth $12,000. So this is the initial price. And also you have to calculate how much will it be worth when it's 10 years old. So part of the problem is to state the variables that you have and to interpret the information that you're given. The solution starts by defining a function d of x, which is just the value of the machine when it's x years old. That is a pretty intuitive variable to define. Now, the second part of information is what you were given was not b, but the rate. So what you know actually is that db over dx is 220 times x minus 10. So that is the piece of information that ties it to our topic, because in order to find b, we have to integrate. Moreover, before we even do a calculation, you can see that this derivative vanishes at x equal to 10. So the rate of change, say, of a car is 0 at that value. Just keep it in mind because we will do an interpretation of the plus later. So this is just, I mean, it can be any machine. It doesn't have to be a car, but I think that is just the easiest concept for which to make it relatable. It can be a printer, it can be whatever. So if you notice, actually, this is the DFQ of the problem. Okay? This is the equation that relates the dependent variable, which is the value of the machine, with respect to the independent variable, which is the time. And of course, in order to solve it, you have to integrate. So b of x is the integral of db over dx, which is the integral of 220 x minus 10 dx. So you take out the constant of integration, and then you have x squared over 2 minus 10x plus the constant of integration, right? Same example that you did. I just took out the constant, and I have the constant of integration to be defined because this is an indefinite integral. Of course, if I want to introduce the particular conditions that I was given before, I will have to determine C. So there is a note that might be helpful for the problem. If you actually evaluate B at 0, this being a polynomial, this whole term vanishes and you have C. So actually C has an interpretation, which is that it is the initial value of the machine. That makes sense, right? That is helpful. Is there any question at this point, or are you guys following? Okay. So we're going to use a letter to represent this, given the interpretation of initial value. So basically, let's denote the constant C by B naught, right? Because you know this. So it's just notation. So if you want to express it mathematically, B of x as a function of x, where x is the time, blah, blah, blah. So you have 220 x squared over 2 minus 10x plus a constant B naught. And this is actually the general solution. Of course, because, well, B naught is a constant to be determined from the particular conditions. Say an initial condition in this case, because actually x is a time. You were actually given also some information, which if machine was originally worth $12,000, so you will relate that over here. If B naught, which we know that is the initial value of the machine from this, which was the C, is equal to 12,000, then the particular solution is, and you just plug in, right? B of x equal to 220 x squared over 2 minus 10x plus 12,000. So, well, I could do the multiplications if you want, that's not a problem. That is basically dividing by 2, 110 x squared. Then I have 2200 x plus 12,000. It's just doing this multiplication. So, of course, now we're going to evaluate, right? So, because that was part of the question. When the machine is 10 years old, so that means that x is equal to 10 because the units are years. Its value will be, so you just plug in the 10, right? B of 10 equal to 110, then 10 squared, you add two zeros, minus 2, 2, 0, 0, 0, plus 12,000, right? So if you do the addition of these, you get 23 minus 22,000, so you get 1,000. So I just plug in the 10. Okay, so far we passed from the general solution. Here we applied, well, from general solution to particular solution to figure out the value at 10. There is a terminology which might be useful when you study minus the derivative of b with respect to x, because notice that, well, the price is decreasing, right? So the slope is going to be negative. So that's why you take the negative of this to have a positive number. So minus dv over dx is called the rate of depreciation. Totally makes sense if you're an insurance agent or a car salesman. In our case, R, just by the formula, is minus 220 x minus 10. Now, I brought up the point of where the derivative vanishes because we will do plots of b and of b prime, or R equivalently. So just to define it, R is the negative of the rate of change of the resale value of the machine. And, okay, we'll keep this here. I will do some plots. have enough space in this one too. Well, have you finished copying? Can I take this page? Yes or no? Well, okay. Let me just do it here. So I will do a couple plots related to the information that we have. So we knew that the initial value was 12,000. Here you have the time, which is represented by the variable x. Then you have b of x, which is what we will represent. You, after your calculation, saw that the value after 10 years will be 1,000. So let's say that this will be x equal to 10. And if you look at the function, it's basically a parabola, right? Moreover, and that's why I kept bringing up this info, at x equal to 10, the derivative is 0. So you know what is a parabola. Basically, it's where you have the minimum. Well, cars never increase their price, so probably that is the limit of validity of the model, because the next thing for the parabola when you achieve the minimum is to go on up. So the model would not make any sense for x greater than 10 years. That is clear. Price always decreases, unless it becomes virtually invaluable, right? Well, so just drawing this parabola, let's say that you have this minimum at this point, and then you have this, and you know that the rate of change is decreasing at the initial time. So basically, well, this is a very flat parabola that looks a little bit like this, right? Initial price, decreasing on the price, this is where the minimum of the parabola is. Because b prime is equal to 0 at x equal to 10. So this is where you have the horizontal slope. So this would be a plot of b of x. Moreover, if you do the computation, well, actually you don't need to do any computation for r, because you know from the beginning that is minus b prime. And that would be equal to minus 220 x minus 10. So if you do a computation actually of the derivative, or minus the derivative at the initial time, which would give you, well, the second coefficient, and you know that at 10 you have that r is equal to 0. Basically, since the function is linear, you only have to join these 2 points. The surface is not perfectly flat, so well, this line will do, right? This is a linear function that takes this value at the initial time, and at 10 is equal to 0, and x is in years. So again, just a little note, notice that r evaluated at 10 is equal to 0 because of this. So that's why I drew this, and it's just linear function. But okay, this might come in handy. I would basically put this as the limit of validity of the model. And again, part of the story is to tell you, well, at least for baby problems, you have solved some DFQs. So usually in an ordinary differential equation course, what happens is that you increase the complexity of the problem. And these are the same problems that you start from in a second year OE course. The next kind of problem, which is also what we're going to see here, is called a separable differential equation. And again, basically, by integration, learned in a calculus course, you can get by to solve those problems. So we're still in the range where our tools are powerful to solve the problem. So the next topic is separable differential equations. And we'll make a definition. So it is a differential equation, and if it can be written in the form dy over dx as the ratio of a function of x and another function of y, why do you think it is separable? Because we can do kind of like the same stuff that we did when integrating, which is pass the x variables to one side, pass the y variables to the other side, and just integrate. So again, we're building over the blocks that we have developed in the previous part of the course. So if you have an equation of this form, is said to be separable. Just, well, if you have an equation of the form, it is separable, then the general solution of such an equation can be obtained by separating variables and integrating on both sides. So, well, pass g on one side and then the dx on the other and integrate. This is literally also what is done in a second-year ODE course. The fact that it's separable expresses this ratio, of course. It means that you can separate the variables onto different sides and just perform the integration. And as long as g and h are not too complicated, perhaps you will not obtain a solution of the form y equal to x, but you will obtain a solution in the form of a curve, which is f of xy equal to c, as the little curves that we dealt before. So again, look, it begins easy, the topic is not easy, just to let you know, as a heads up. Please take your time reviewing the concepts, because you have to learn new terminology, you will deal with more complicated problems later on, so just keep that in mind. So the next one is a physics problem, using the velocity to study the motion of an object. The information is that the object moves along the x-axis, meaning that the movement is in one dimension, in such a way that at each time t, its velocity is given by the dpq dx over dt equal to x squared natural log of t. So, again, for calculus, the problem of the velocity of a particle, even if it's in 1D, is basically the fundamental stone over which the concepts will be. Because essentially Newton built the calculus after this story of the apple falling from the tree, which is a motion in 1D. For that you have to solve a differential equation, even if it's the simplest dpq, which means that you have to pose the problem in terms of acceleration, velocity, position, second derivative, first derivative, the function. You have to integrate, and then from that you make a jump in physics to study the motion of the planets. And for that, the problem is more complicated, it's in 2D, etc., etc. But what you're seeing very quickly in this course is the evolution of physics in that time, and how you went from assuming that the motion of the planets is done by angels to at least have a model that represents how it's happened. You might not know why it happens, but you know that it happens. So I'll just finish putting the statement and probably we'll finish the class. So that is the dpq. And if the object is at x equal to minus 2 when t equal to 1, where is it when t is equal to 3? So, having said that, before we solve the problem, look, notice what the kind of condition we have. This is basically an initial condition, because what it's telling you is that the position at time 1 is equal to minus 2. This is the initial condition. This is where you start from. So now the interpretation makes more sense in this. If the independent variable is the time and the dependent is the position, this is the position at the initial time, so-called initial condition. What you want to do is to predict by solving this DFQ, which means by integrating this equation, what is the position at x of 3. Basically what they're asking you is x of 3. So that is the statement. Keep it in mind, and we will start with the solution on next class. So good luck.